Continue on physical chemistry, chapter 12. We're in section 2 now. The first colligative property we're going to talk about is vapor pressure lowering. Now we're going to assume for now that we have a non-volatile solute, which means it's not going to vaporize, it's all solid or liquid form, but no gas. So the pressure of the solution then is due to the solvent only. So the pressure of the solution is equal to the pressure of A, which means our solvent, which is equal to gamma of the A, our solvent, times the mole fraction of A, the solvent, times PA star, so the partial pressure of the solvent only. And this is be for any solution as long as our solute is non-volatile. Remember, gamma A is our solvent activity coefficient. So let's also assume for now that the solute does not break into ions. Then the activity of A is going to be equal to gamma of A times the mole fraction of A. And remember, gamma of A is equal to 1 if you have a non-electrolyte. So let's say that we have glucose, which is C6H12O6. Sucrose would be C12H22O11. So the change in pressure, remember this is our vapor pressure lowering, that's going to be equal to the pressure of the solution minus the pressure of the solvent when it was pure. So that's going to be equal to gamma A times the mole fraction of A times PA star minus PA star, which is, factor out the PA star, you're going to have gamma A times chi A, so and minus 1 times PA star. So the change in pressure is going to be gamma A times chi A minus 1. So the activity coefficient times the mole fraction minus 1 times PA star. Now remember, like I said, gamma A is equal to 1 for an ideal or an ideally dilute solution. So first, let's say we have an ideally dilute solution. Then we're going to say gamma is equal to 1. The change in pressure is equal to the mole fraction minus 1 times PA star, and that's going to be equal to minus the mole fraction of the substance times PA star. The reason we say a minus sign, of course, is it's decreasing. Now this is only for a two-component solution. Okay, so look at this graph. Here's the change in pressure. There's no x-axis. This should probably be mole fraction on the x-axis. Oops. Okay, so if we have an ideally dilute solution, no matter how much we add, the change in pressure is going to be 0 because there's no reason for it to change. If you have an ideally dilute solution, it's going to curve down. So the more you add, the lower the pressure is going to be, the bigger the change in pressure is going to be. So the slope here is equal to minus PA star because of that graph here. Yeah, and then this curve here, the solid curve, this is what happens with a real solution. So this graph, though, it applies to any solute. So the change in pressure is independent of the nature of B, and it depends only on its mole fraction, the number of solute particles in the solution. Now, departure from ideal is based on the number of solute particles, not their identity, just like with electrolytes. Remember, with electrolytes, we showed how it broke into ions, and the more ions, the more deviation. At low concentration, a real solution behaves like an ideally dilute solution. All colligative properties depend on the quantity, not the nature, of the solute particles. That's all for section 2.